for attending. Today we have a session on the exciting area of design of materials and structures. There's been a lot of recent developments in the area and things like topology optimization, additive manufacturing, and of course machine learning, neural networks, Bayesian optimization, and these things. And we've got a nice cross section of papers from the past couple of years, excellent papers that were selected to be presented to you today. Carolyn, I'm not sure if you would like to add anything now with regards to the session.
Well, sure. Thanks, Doug. First, I just want to thank Fayez and Doug and Chique for organizing this session. They've done a great job. And of course, this is our 12th of these sessions. I started under my predecessor, Wei Chen, who had a wonderful idea to get these started during COVID, and we've continued them as a way to help build, community across the world of people who are able to join these webinars. So I just really want to thank the organizers and the speakers and also the support that we've gotten from ASME. And we also have a really excellent new assistant, Regina, who I think will be joining us in a few minutes, and want to thank her for her help as well. But just wanted to say welcome to everyone. I'm really excited to hear these talks. And I'll turn it back over to Doug and Chique and Fayez.
All right, well, thank you very much. And so, like I said, we have 4 talks, and each will be about 10 to 15 minutes long. We'll reserve questions until the end. And at the end, there'll also be a gather.town hall event. I think Fayez will be able to give more information regarding that, perhaps at the end. So with that, I think we can begin. The first talk will be Dr. Shea, is that correct? We'll turn over the floor to you, Dr. Shea.
Thank you. Let me just share my slides. Good. Yes, thank you for inviting me to present this paper. It's work that was done by a former PhD student of mine, Thomas Lumpe, who, fortunate for him, is on vacation this week, and unfortunate for us. And so I will present it on computational design of multi-state lattice structures with finite mechanisms for shape morphing. So in our lab, we do a number of different pieces of work, and this work is focusing more on what we started in terms of combining computational design algorithms with fabrication and testing of them, mostly around using 3D printing. And his project was part of this, looking actually at 4D printing. And so this middle part are 4D printed lattice structures that are optimized and printed and tested, which was also part of this work. And the work that's in this paper is rather a different approach to active structures and to shape morphing. And so active structures are used many places in society that we've seen. For example, being able to change the position of solar panels, or we all know the different moving parts and flaps that move in airplanes, or even on building facades, for example, for the alternating the shading and the lighting in a building. And so in his work, what he was looking at is different ways to provide these types of active structures and shape morphing in a way where to try to have maybe a simpler way to look at this, rather than the traditional complex assemblies that are heavy, have high maintenance, error prone, and where the function is often decoupled from the structure itself. So the structure is usually designed, and second, it's then activated. And the goal here was to be able to integrate the functionalities of the shape morphing directly into the structural design, and also to try to require fewer actuators, or even in the 4D printing case, no actuators. So in this paper, he looked at kinematic shape morphing, and I'll just review a few principles here, but not go into them in detail. So we all know that we can look at lattice structures, and they can be rigid, and this rigidity is defined by Maxwell's rule. And if we look at, for example, the structure that you see here, we have just a simple structure with two supports, two bars, and it's statically and kinematically determinate. And then we can have a finite mechanism, but just by changing the support location, support in the right-hand side to a roller rather than a fixed support. And that gives us this finite mechanism of m equals 1. If we look at this a little bit further, what we get is it's defined by the equilibrium matrix. And so we have an update of this mechanism rule so that we can be able, so what we're looking for is a way to be able to determine, given a lattice structure, how many mechanisms does it have. And so this is a function of the equilibrium matrix, is a function of the node positions and the connectivity, which is what he uses in his optimization problem. So he looks at two different ways of determining the kinematic behavior. And in this, there's I will just click through this a bit. It's all based on 3 papers from Pellegrino, Calladine, and Kumar. And so he implemented this. So he carries it out 2 different analysis simulations. The first is a linear simulation. So we have the same mechanism here, and we have the roller on this side. And so we can find the displacements, the linear displacements. And then we could also use a update. So if we have a bar and the bar is actually moving along a kinematic path, we would have a linear deformation of the point in that direction, and we need to correct it back to the kinematic path. So these are 2 ways to look at the kinematic behavior that he incorporates into the optimization model. And it's really all based on these other papers. So I would say it's not the core contribution of the work. And so an optimization problem is set up for this. So in the optimization problem, we want to take a ground structure that you see here at the bottom. This is a morphing wing. So the ground structure is defined. We have a certain target displacement that we want to achieve. And this target displacement is defined as a series of joints and their deflection. So all of the yellow triangles are the deflected joints. And we compare this current deflection to the target, and that is what we're trying to minimize. So it's really a constraint satisfaction problem. We can then define certain things on our structure. So for example, we can define ranges within which a node can move. And we, in this case, look at almost all mechanisms with just 1 degree of freedom. So we want to have just 1 input actuation. So there would be an actuator here that results in the target deformation. We can also say that nodes are fixed in space. So all the nodes with the blue are nodes that are fixed in space in the problem. And so this sets up an optimization problem that's a combined continuous optimization of the joints that can move, as well as a discrete optimization of the connectivity of the bars in the structure. So he sets up the optimization problem, and then the optimization is carried out in 2 steps. One is optimization via the linear subspace analysis that I summarized in the last slide. And the second one is the nonlinear kinematic simulation. Both were carried out by genetic algorithms in MATLAB. He did try pattern search as well, and then found in this case that the genetic algorithm performed better. So I'll move now to examples, because I want to show you also the results as well as the link to the experimentation. And so the first example is a force inverter. Many of you have probably seen this in the literature. And so what it is so on the left-hand side here, we have a half symmetry ground structure that we'll start with. So we apply a force here on the lower left support, and we'd like to have a deflection here on the lower right in the opposite direction. And so that's this force inverter problem. So as I said before, all bars can remain present or be removed. The 2 central nodes, so these that have the blue bars, so these can move within this bounding box. All other node locations remain unchanged, and this half symmetry is used. So now I'll just show you the video. And so what you see here is it's in black, but it's actually, he's pushing, this is the degree of freedom. So these structures have 1 degree of freedom. And so when you push it and actuate it, I can just play that again, maybe. When you push it and actuate it, then it results in the right target displacement. So, and also the error. So the mean error is calculated for each target displacement node. It's 0.24 millimeters in this case. The second example is a gripper example. So in this example, it's the same. All bars can remain present or be removed in the first part of the problem. The blue nodes, if I click through, remain unchanged. In this case, it's just a few of them. Some nodes can only move within a bounding box. And in this case, what we have is we have an input deflection here, and we want the gripper to move in this direction here, the UT. To be able to grip an object. Again, half symmetry is used in this problem. So this is the resulting structure, and it moves to the target nodes that it should. And it was carried out also in experiment. And if you look carefully, what you'll see is here we're pulling in using this lever, and then it's gripping the object over here. So in this case, also the accuracy between the theoretical optimized structure and the experimental is good. So the next example, if I still have time, is the airfoil example. So again, we have a ground structure. We have 1 degree of freedom input. These yellow triangles are the target nodes. The blue, again, don't move, so it's a very similar setup. And what you see here at the bottom is the optimization results, so the input and the resulting structure. And I'll show you also the experiment, which has, again, a lever pushing in, so this 1 degree of freedom, and it achieves the target displacement here at the bottom. And the accuracy, again, between the experimental and the optimized structure are very good. So deformation is controlled by 1 degree of freedom. Structure becomes statically and kinematically determinate when this is fixed. So for example, if we fix this 1 input node, and it's fully reversible as well. So yeah, so there's the mean experimental error there, 1.58 millimeters. So the last 2 examples I want to show quickly would be target path. So this is the next update to the optimization problem. So rather than a target deformation of a structure, we have a path we want to achieve of the tip of this structure, and it changes the optimization model a bit, and the details are in the paper. And then again, you see here the link between the optimized structure, and then you see moving the white, the experimental structure by pushing in at this 1 degree of freedom. And the last example is a multi-state solar collector. So this has 2 different states. So now we have M equals 2, so 2 mechanisms. And the goal here is that with 1 structure that we've optimized, we can create a structure that can slant the solar panel in 1 direction if we push on this side, and then in the other direction if we push on the opposite side. But it has to be 1 structure. So 2 degrees of freedom, but 1 structure. I'll just show the video for that one to show that it works. And you'll see the push from both sides so that it goes in both directions. Okay, I think that I'm out of time almost. The prototyping is extremely important here. And a lot of work went into behind the scenes, making these prototypes monolithically and being able to print them using 3D printing to be able to achieve the results and match the simulation to the real. So these are tailored designs that enable this kinematic shape changes. The deflection is coupled to the input and is reversible, multiple target states for multiple inputs, and a framework is provided to be able to do this. And to be able to match to the experimental, a lot of work went into also the multi-material 3D printing and being able to achieve that. And the applications for this are in, for example, in aircraft wings or building facades. So I will end with that and hope I stuck to the time. Thank you very much for your attention.
Yeah, thank you. Thank you, Dr. Shea. Is there any question from the audience? Or if there's no question, or we can keep all the question and answer at the end of the webinar. Okay. So so the next speaker will be Dr. Nathan Hertlein from the Air Force Research Laboratory, and he will share his research on design optimization of lattice structure on the impact loading for additive manufacturing. So without further ado, please.
All right, great. Yeah, hopefully my screen is sharing properly. If not, feel free to just let me know. Yeah, so like mentioned, my name's Nate Hertlein, and going to be talking about lattice structure optimization under impact loading, at least with some eye towards additive. This work was done during my time at the University of Cincinnati, where I did my PhD, along with professors Kumar, Vemaganti, and Sam Anand. So yeah, thank you for the invite to present this. It's been enjoyable to look back at it again, and yeah, looking forward to talking about it. So I've since my time at UC, I moved on to the Air Force Research Lab, and Professor Vemaganti also moved on to Sandia National Labs. I thought I'd take just a quick second here to give a quick overview of some of my current research interests. Oops, here, see, I got the wrong button here. Okay, hopefully the slide will advance. There we go. Yeah, so very much along the lines of what you'll hear today. You know, I'm interested in design optimization, design for manufacturing.
Nate, I don't see the slides.
Oh, I completely made it go away. Sorry about that.
No worries.
All right.
Yep.
Okay.
So,
Cool. Thanks. Yeah, so design optimization, design for manufacturing, definitely some work in IDTC that I wanted to show down there, just using generative adversarial networks for topology optimization type of problems, which can have some interesting results when you turn on and off things like additive manufacturing filters. And then also kind of a growing field of interest now in robotics and natural language. So taking things like natural language instructions and using various forms of reasoning to get to like physical execution of those instructions in the physical world. Driven largely by a new lab that the team that I'm on has just opened up, led by Dr. Sean Donegan, the Collaborative Automation for Manufacturing Systems Lab. Yeah, just a lot of cool hardware, so want to get into those things as well. But yeah, love to chat. Definitely feel free to reach out anytime. But yeah, oh man, I'm doing it again. Here we go. Let's see here. Hide. Okay. Hopefully that's right. So quick background then on the work for today. So originally started out in automotive engineering in occupant restraints. They do all kinds of impact tests in that field, as you can imagine. I just showed a picture of one here where they stick a head form inside a car and launch it at the side of the car. And they essentially take measurements of the acceleration inside that head form as it comes into contact with pretty much any part of the car. Usually they'll take that acceleration curve and boil it down to some scalar injury metrics or injury criteria. I've listed a few there. There's a whole bunch. I'll mention one a little bit later in more detail. So yeah, definitely that kind of got me interested in topology optimization or design optimization for impact loading. So when I got back to school, starting my PhD, I started looking at the literature and noticed there's a lot of work in lattice structure optimization for additive, showing a bit of it here, which yeah, does a great job, but the loading is usually quasi-static in that work. There's also some work in topology optimization for impact loading, some of which I've shown here. The loading there, it captures the dynamic effects, but there's not as much consideration for the additive process. And I'd also be interested in tying things as closely as possible directly to the injury metrics. So yeah, that was kind of the bit of the motivation. Okay, first time I advanced the slide without throwing it off. Getting better. So typical approach for something like this, you have a problem definition, which I've shown on the left, which is a design domain, and maybe there's some a rigid wall that I'm showing up top, which has a mass and an initial velocity. And you might want to minimize things like the volume or the mass, which is obviously important in transportation in general. And then also some kind of injury metric like head injury criterion or HIC, subject to something about manufacturability. Typical approach for this could be along the lines of what these folks did here that I just decided to show as an example. So yeah, they start with the lattice structure infill, and they have a unit cell design, which is parameterized with a small number of design variables, perform a whole bunch of simulations in that design space, essentially a DOE, which enables them to build a response surface. They were looking at energy dissipation as the response. And then you can go to the minimum on that response surface, and that's kind of the optimum. But what I was interested in is, can we somehow get out of the requirement for a rectangular envelope and make it a little bit more injury relevant? And can we consider the build process, at least to some degree? The difficulty that comes out pretty quickly in that would be how to parameterize the design in a way that's low enough in dimensionality to handle, but also general in the sense that you don't need to be just a rectangle. So yeah, I will this is the overall approach that we took. It's a lot going on, so I'll kind of step through it just step by step. And yeah, then I'll show some results at the end. So yeah, going first, what we do in these first couple steps is we take essentially that problem definition with the moving mass with an initial velocity, and we convert that to static loading. So just like a static pressure, in this case on the top of the design domain. That enables us then to run traditional density-based topology optimization, SIMP. So we just use the 99-line code for that. And then we can filter against overhangs, kind of targeting an additive process using Langlar's overhang filter. That gives us a density field. And if we essentially draw a line at a threshold in that density field, some threshold rho, that will give us an overall envelope of where the lattice structure could be, which essentially, this looks at the heuristic that regions that are important for carrying a static load are probably also to some degree important in carrying or dissipating an impact load. Yeah, where that value rho will come up later as a design variable that we want to optimally select. Okay, so that gives us the overall envelope, which is not necessarily rectangular. How do we fill it with a lattice structure? So that's kind of the next step. So what I'll show here on the top, we'll see just kind of an example of a SIMP density field being filled in with the lattice structure. We're going to look at two different unit cells. One is the diamond, and one is a hexagon, both of which are parameterized according to 3 different design variables, which are illustrated here. Yeah, and we want to pick the values of those design variables. I'll just note too that the values that they can take on are constrained based on design for additive considerations. So for example, overhangs are kept to be less than 45 degrees by constraining the ratio in the case of the diamond of x1 and x2. And in the case of the hexagon of just the value x2, thicknesses are also constrained to be no less than 1 millimeter, which is kind of a rule of thumb for additive, very rough. Yeah, this represents essentially what you could call like the mesostructure of the design. All right, so at this point then we have a lattice structure, which is not necessarily rectangular. It's filled in now with unit cells that are, their design is parameterized. What we'll do next is send that through an actual like high strain rate finite element simulation. So for this step, we used LS-DYNA, and it was a really great learning experience, I think, because there's so many different aspects of a simulation like this to set up. So I'll just talk through them pretty quickly. Full details in the paper, but obviously there's some loading and boundary conditions that you start with. We'll consider, like I said, a moving mass. Material properties we set from values in the literature for 316 that had been SLM'd, which has been shown to have under high strain rates, a Cowper-Simons strain rate sensitivity, which we include in the model. Did some convergence studies on the mesh. We used beam elements, as you can see here. So yeah, figure out how many elements we need based on the size of the lattice unit cells. Mass scaling is definitely a factor in these types of simulations. It helps accelerate the solution convergence. But if you use too much, then you can lose accuracy. So we had to figure out how to tune that on an example problem before we go into kind of the loop. The objective function I'll zoom into for just a quick second here, since there's a couple parts of it. So on the one hand, I mentioned typically we want to keep mass low or weight low. So yeah, volume is one of the objectives that we want to essentially minimize. The other one is the head injury criterion. So this is one of those scalar metrics that get pulled from the acceleration curve. There's the equation there. Essentially, it becomes a large value if you have a huge peak in acceleration or if the acceleration is sustained for a long period of time, and you want to minimize that. Side note that we had to include a penalty for designs that didn't actually fully dissipate the velocity of the moving mass. So some really thin designs, the mass would just move through them and keep right on going, which gives a good Hick value, but obviously doesn't dissipate the impact properly. So yeah, we developed this term here, which is essentially the remaining kinetic energy of the wall penalized, or I should say scaled by this parameter P, which requires some tuning. But yeah, it's basically our two objectives then, is volume and Hick. All right, so now we have a design. Our first design, at least, we can evaluate it, pull off the objective from that simulation. But then how do we know how to pick our next design to evaluate in the loop? So that's where Bayesian optimization comes in. The way, I'll probably just kind of gloss over this, but essentially you train a Gaussian process surrogate model on the data that you have so far, which has a part of that is a covariance function, which has another parameter that needs to be tuned. In our case, since we're using the Mayturn class. And then you evaluate on that surrogate an acquisition function. And I mentioned that we had kind of a by objective optimization problem. And rather than scalarizing, which is often done, we did choose to look at an actual by objective optimization. For that, we needed a acquisition function that actually targets not just improving one objective, but actually improving the Pareto frontier, the set of trade-offs between those two objectives. So for that, we use the hypervolume-based probability of improvement. Yeah, so basically, the next design is selected in such a way that it will maximize the probability of improving that Pareto frontier. So that's pretty much how the overall flow of things goes. Now just kind of quickly talk through some examples. So actually first, I mentioned a few parameters that needed to be tuned. We did that tuning by running Bayesian optimization on some unit cells, just each unit cell on their own. The Pareto fronts that we got here, are shown here for two different build direction assumptions. One being the south, which is in black, one being the left-hand side, which is in gray. Yeah, so no sim subloop here, just Bayesian optimization on the units. That gave us values for our hyperparameters that performed well. And then the example problems that we looked at are shown here. We looked at two, basically moving mass, and it's either fixed in the bottom corners or the top corners. And we looked at three different build orientation assumptions. And I'm showing the best of, it was either 2 or 3 runs, I think, that are shown here for those 3 different build directions in the 3 different colors. The circled points on the graph on the left are shown to scale in the middle. And I should note too, we included an additional design variable, which was essentially a scalar to multiply the design domain size by in order to really see some interesting trade-offs between Hick and volume. And yeah, so you can kind of see what you might expect, that designs with lower volume have higher Hick and vice versa. What I thought was really interesting is the qualitative differences that you see in the designs that come out based on the build orientation assumption. So when your build plate is on the top, in the example on the orange on the right-hand side, you get very different shapes than when it's on the bottom. This is for the diamond unit cell. The hexagonal unit cell is shown on this slide, similar observations. And then, yeah, the second example problem where it's fixed in the top 2 corners, similar thing where you see these qualitative changes in shape based on the build orientation. Yeah, and then the last unit cell is shown here. So yeah, just to quickly wrap up, I think, definitely a lot of room to go here. You probably noticed that there's a lot of local optimality still. These Pareto frontiers are by no means, necessarily or like proven to be full or thorough. So yeah, I think there's definitely some non-convexity in the objective function that could be an interesting thing to sort of dig into a little bit more. But yeah, also future directions could include one thing that I've been thinking about is, could generative modeling maybe help with generating design candidates for a problem like this, given that the objective function is so non-convex? Maybe we should take a different approach in the future. But yeah, that's pretty much an overview of this work. Thank you for the time, and yep, appreciate it very much.
Okay, thank you very much. Our next talk will be by Andres Tovar from Purdue. He'll be talking to us about some aspects of neural networks within topology optimization. Andres?
We cannot hear you, Andres.
Okay.
Yep. Works now.
Good. Well, our lab works in applications of machine learning to help design, in particular design optimization. We have seen several contributions in the in methods to obtain derivatives of the outcomes of neural networks, and we see an opportunity to use those methods and help gradient-based optimization, so we can ease the cost of the sensitivity analysis. Our work explores 4 derivative methods that are used in neural networks: automatic differentiation, analytical, so the analytical neural network Jacobian, which is just the application of the chain rule on the activation functions of the nodes, and 2 numerical methods, central finite difference methods and complex methods that are applied directly on the output of the network. This work was done by my former PhD student, so that would be Dr. Joel Neyman, who currently works for the US Army. I'm sorry, US Navy. The main application of this work is in topology optimization. So we apply the method and we study applications in density-based topology optimization. These are 2 examples of density-based topology optimization application of neural networks on that, and homogenization-based topology optimization. In both cases, the neural network, there are neural networks that are trained to directly obtain the sensitivity information. So we have, for instance, in this paper, the sensitivity information is an input that is used to train the neural network, and the neural network can then predict that outcome. They use convolutional networks, but most commonly, the architecture is MLP, is a multi-layer perceptron. That's the most common type of architecture. Also, instead of training the neural network to get the sensitivity coefficients, they use automatic differentiation, and that is pretty much what the state of the art is in the application of the networks. For homogenization-based topology optimization, the neural network is trained to find the derivatives. So this one would be the derivative of the objective function with respect to the design variables, and the design variables correspond in this paper to the size, to the radii and the orientation of the void inside a cell. And they do that also in 3D. There are two papers that I wanted to include in this presentation, published in 2022 and 2021. And those ones contain a pretty good summary of papers that use neural network in topology optimization. So there are like two families of applications. One family uses convolutional neural networks and GANs, generative adversarial networks. And these applications are for generative, non-iterative topology optimization. So that's like one family. And then the other family is the use of multi-layer perceptrons. And with the aid of automatic differentiation, usually automatic differentiation, they just ease the cost of the sensitivity analysis, and that helps topology optimization. So, in summary, the neural network, which is in most cases a multi-layer perceptron, is trained to predict directly the sensitivity analysis, but in some cases, the sensitivity analysis is obtained using automatic differentiation. For homogenization-based topology optimization, the neural network also predicts the homogenized properties, and the network is trained to find the sensitivity analysis of the objective function with respect to the microstructure design variables. What we have not seen is a paper that directly compares the performance of different derivative methods, which include also methods that have been established not for topology optimization or not for use in gradient-based optimization, but have been available to do backpropagation and just training the network. So what we did in this paper is that we took some of those methods and we just extend their use in these two types of applications, density-based and homogenization-based topology optimization. The network that we use is a multi-layer perceptron. So it's a classic architecture. The input layer for density-based topology optimization, the number of input layers is 1, and that represents just the density of the element. For homogenization-based topology optimization is 2, and the type of microstructural model that we use is a element with a rectangular void. And the 2 input nodes represent the width and the height of the rectangular hole. The output layer for density-based topology optimization is just 1, and that is the prediction of the Young's modulus. So we can directly compare. So we obtain, using this solid isotropic material with penalization. This is the modified version of the SIMP model. So we use that formula as input for training. And then the advantage of this one is that the derivative has an analytic expression that we can use for ground truth for comparison. For homogenization-based topology optimization, the output layer has 4 nodes, and the 4 nodes corresponds to the 4 elastic coefficients of the stiffness matrix for an orthotropic material. And we obtain those ones numerically using the usual 3 reference strains. And that allows us to calculate the the derivative of the objective function, and the objective function that we are using in this paper is the traditional compliance. So in order to obtain this derivative, we have to find out what is the partial derivative of the stiffness tensor with respect to the design variables. And this derivative depends on the derivative of the elastic coefficients with respect to the design variables. So the method works as follows. We still need to use finite element analysis. We have not replaced that one with a neural network. There is an opportunity also to ease out the cost of the analysis, but we still use it. What the neural network does is that it predicts two things. One is the stiffness matrix, or it predicts the homogenized properties of the microstructures for homogenization-based topology optimization. For density-based topology optimization, this is just corresponds to one single value, which is the Young's modulus. And we also predict the sensitivity of the stiffness tensor with respect to the two design variables, the design variables that define the microstructure. And we do that using the 4 approaches, which is the automatic differentiation, the analytical neural network Jacobian, and the complex step method, and the central differences. And with that, we obtain finally the sensitivity coefficients, which are used in conjunction with the objective function to update the design variables, and this process continues. We apply the process to a traditional topology optimization in 2 dimensions. This would be the initial design for density-based topology optimization, and then we have an initial design for homogenization-based topology optimization. So the results for density-based topology optimization, we compare the final topologies with the ones that we obtained using SIMP. And this represents the error between all the approaches. So we have SIMP, the neural network Jacobian, the central finite difference method, and the complex step method. So the error between all of them shows that the central difference, which is applied in the output of the neural network, is the one that is more different than the other ones. And if we see at the plot of the iterations, this is a convergence plot versus the compliance, this is the objective function, we observe that the complex step method right here is the one that has the different path for convergence, and it also produces a somewhat different topology. Not too different. The mean square error is still pretty low when we compare with the other ones, but it's the one that is more different. We observe the same trend in homogenization-based topology optimization. So we don't have a SIMP in this case. There is no, in a way, ground truth for comparison, but we compare the different topologies among themselves. It's the same idea. The ones that are closer to each other, with each automatic differentiation and the neural network Jacobian, which in fact they should be so close, they should be similar, very similar, because the principle that they use is the same. It's just a chain rule applied over the activation functions of the nodes. It's just that this one is done analytically and this one is done algorithmically, but they should really produce very close results. We see that the path, the convergence path that they take, both of them, they are pretty much overlapped. You cannot even see the blue in here, and then the results are also the same. The one that is a little bit more different is the central difference, this one. And yeah, you see that the error of the central difference, you know, with the other ones, it's higher. And that is also expected because of the convergence path. So in conclusion, all the 4 derivative methods in this research, they obtain final topologies that are very close to each other, very alike. The mean square error, when we compare the difference in the density distribution, is, you know, is pretty low. But there are differences, and the differences, one can, just by looking at the convergence plot, one can observe that the most different ones are the ones that take a different route. So that would be for density-based topology optimization, that would be the complex step method. And for homogenization-based optimization, that would be the central finite difference method. So all the methods, but particularly the neural network Jacobian automatic differentiation, which should produce the pretty close results, and the complex step method, they produce pretty much the exact same coefficients, nearly to working precision of the computer. There is a big difference in terms of the time that it takes for the sensitivity analysis. So neural network Jacobian and artificial neural network, we can say that this is just the application of the chain rule. They take about the same time, you know, over 2.5 seconds in these problems, at least for density base. For homogenization base, the application that we have in TensorFlow takes over 5 seconds. So these 2 methods, which in general are very robust, and they produce good results for both density-based and homogenization-based, they're also computationally more expensive than the other 2. In any case, if we, you know, have to make a recommendation, what we would recommend is to, you know, this, if the computational time is not really a big issue, like this, you know, seconds, this couple seconds is not really a big issue, these would be the 2 best methods because they work very well, you know, in any application. And with that, I'm open to questions after the presentations.
Yeah, thank you. Thank you for sharing with us your wonderful work. So without further ado, let's invite the next speaker. So Professor Raymundo Arroyave from Texas A&M University. So he's an expert in computational material science and data-driven design. So today he will discuss the asynchronous multi-information source Bayesian optimization. So Raymundo, please.
Yes, hi, can you hear me?
Yes.
Okay, so this is again, you know, talk about, you know, using engineering optimization techniques to solve a materials problem. In this case, I'm going to talk about work that has been done with Danial Khatamsaz and Doug Allaire within the context of a lot of our work on the use of Bayesian optimization methods to do material discovery, specifically alloy discovery. So we're interested in trying to navigate very complex chemistry and processing spaces in the metal alloys material space to try to optimize performance under multi-objective settings. So basically, in the context of design, this is, you know, for us material scientists, this is a way for understanding the material space. So in material science, when we teach material science to our students, we always emphasize this, mental map, if you will, on the existence of causal connections, that relate processing, that is anything that you have to do or that you can do on a material to change its configuration, the structure, which is a multi-scale hierarchical definition of the arrangement of materials at all scales, from the atomic level all the way to the microscopic scale. This arrangement, which can be defined in terms of chemistry and different motifs at multiple scales, results in different sets of properties, and the collection of properties can be used to evaluate some type of performance that the material has to have in order to meet some specific technology requirements, right? So when we're doing material science, we typically navigate this process structure property performance relationship in a forward way. When we're trying to do alloy design or alloy discovery, we're trying to solve this inverse problem where we're trying to connect a particular set of performance goals to the ultimate set of processing conditions and specification of chemistry to realize ultimately the properties and performance metrics that we have. So when we're trying to do material discovery, essentially we're trying to navigate this material space with a purpose. This is, however, extremely expensive, right? And, unfortunately, we cannot use traditional approaches to solve this type of inverse problems that you would use in other engineering tasks. Because when we're trying to do this experimentally, sampling, a single point in the material space may take, days, weeks, months at a time, right? So this is a very expensive problem. So, in this context, we're trying to map this discovery process as a black box optimization problem where we're using Bayesian methods. They have been discussed, significantly in this session. We're trying to build some type of stochastic model that predicts the outcome of experiments that we haven't run yet, anchored by some, finite, number of observations. And, these stochastic predictions are then used to construct some type of utility function that can, help us build a policy that prescribes what is the next point in the experimental space that we need to explore. So, in material science, we use multiple ways of looking at materials. We have different types of experimental techniques at our disposal, and we also have different types of models at different levels of fidelity and cost and accuracy. So, thanks to my interactions with Doug, we started exploring the notion of using multi-fidelity Bayesian optimization, where we had different, models or different information sources. This could be experiments or computational, models. And the idea is, how do we use these different information sources in order to fuse them and obtain a better, more precise model of the world that can help us navigate these black box spaces in a more efficient way, right? So multi-fidelity Bayesian optimization is pretty standard technique in the engineering design community, not so much in the context of material science, because our field has come just recently to become aware of these very powerful techniques. So there's a lot of different examples of recently in which people have combined multiple information sources. There's a lot of really nice work out of Sandia where they actually have used multimodal learning to try to navigate very complex materials and structure spaces for optimization. And there's a lot of work that we have done at Texas A&M, particularly with Doug's former student, our current postdoc, Danial Khatamsaz, where we have actually demonstrated the power of using multi-information source Bayesian optimization. I really apologize for the background noise. There's something going on outside my office. I hope that you can hear me. So anyways, we have shown that by combining these multiple information sources that may not really be that accurate relative to the ground truth, we can arrive at optimal solutions, for, some, toy problems in a very efficient way. Now, we have implemented this already in physical experiments. We have a center, so Doug and I are part of a center funded by the Army, where we have actually tried to implement these Bayesian optimization loops to do alloy discovery, where the experimentation step, we actually have multiple types of experiments, right, that tell us different things about the mechanical properties of these materials, and these different techniques have different costs. They take different amount of effort. They can be completed in different amount of different times, right? But we have implemented this type of multi-information source Bayesian optimization approaches to do material discovery, right? And in fact, we have actually shown that using these approaches, we can actually dramatically accelerate the rate of alloy discovery, compared to traditional materials development strategies, right? So we have been able to show orders of magnitude improvements in the rate at which we can explore and exploit material spaces. So everything is fine, right? However, one of the things that we have encountered is the fact that when we're trying to do traditional, Bayesian optimization, that relies on multiple information sources, when we, the steps are as follows. We decide to run, we decide what experiments to run. We run the experiments or simulations. We tend to wait to get the results. So we have a checkpoint, okay, for all the different tasks to be completed. Once, we arrive at once, we wait and we get all the tasks being completed, we move on, we update our model, and we carry out the next iteration, right? So one of the biggest problems that we have in this case is that there are bottlenecks, right? There are experiments that are much more expensive than other experiments. There could be issues with the experimental campaign. Maybe a particular facility that we rely on has to shut down. This center, for example, involves collaborations with two other institutions. We have to ship the samples, right? Maybe something happened to the samples. They're lost, or we have to, repeat the experiments. So there are many things that can go wrong when we're actually trying to do this Bayesian-based, material discovery. So what, Danial, has done with some advice on the part of Doug and I was to try to develop a framework that was robust against this, the need to have these checkpoints, right? So the framework is relatively simple. We start by initializing, some type of a stochastic model, in this case, a Gaussian process model that, is the model of the world. We pick the information sources that we know can be completed in the remaining time that we have for a particular cycle. We search for the best experiments from the information sources that we have picked that can be completed. These are the information sources that perhaps can, happen at, small experimental cost. We trigger the experiments and we move on. And if they're, in this case, we were doing this, experiment in an actual computer, and we were actually trying to allocate compute resources from a particular node, right? But you can imagine that this can be translated to a real, material discovery problem. What we did, in order to carry out this, asynchronous Bayesian optimization is to augment the expected outcome of experiments that we hadn't run yet by, using the current information to predict the mean response plus the expected improvement, right? And, what we did in this case was to consider that the ground truth was the bottleneck. If we felt that there was time, to query the ground truth, we queried it, we fused information, and then, we kept carrying on in our optimization, right? So every time in principle, in the framework, we can accommodate for the fact that at some point during the campaign, some new information may come. Essentially, what we do is we update that model, we propagate the updating of the model throughout our Bayesian optimization scheme, and we keep going until we either meet the our objectives or exhaust the resources available for a particular campaign. So this is how it works in a toy model. So, in this particular case, we have a ground truth, and then we have two different information sources. And here we're trying to solve an optimization problem where, we're actually trying, to evaluate this synchronous Bayesian optimization versus the asynchronous Bayesian optimization strategy. And we're looking at how efficiently we actually minimize a particular function. Clearly, the asynchronous Bayesian optimizer for the same time elapsed in a particular optimization campaign is superior at finding the best answer. Importantly, there is less variance in the performance of the optimizer regardless of where we start. So that means that this asynchronous Bayesian optimization scheme is not only more efficient, but it's also more robust. And, at the bottom here, we can see that the actual protocol by which different information sources are selected is different depending on whether we're following asynchronous or an asynchronous technique, right? So clearly, not only are we, making, the use of resources, more efficient, but in reality, the way in which different information sources are queried also changes when we have, these capabilities. Notice also that the models are called a lot more often when we're doing asynchronous Bayesian optimization than when we're doing synchronous Bayesian optimization, because we do not have this idle time. We did another example where we looked at a material science example where we have a particular mechanics model or different types of mechanics models. We have a multi-phase material, and we're trying to optimize the microstructure of this material in order to optimize a particular measure of mechanical performance. Here we observe, a similar trend, right? We get, in this case, we're not on this plot. I hope that you see my pointer. What we are plotting is the design, parameter, the optimal design parameter, microstructure feature that optimizes the property of the material. We arrive at this optimal feature much faster than with synchronous optimization, and the standard deviation is also small, much smaller. We can also see that different sources are queried a lot more than when we do a synchronous BO versus synchronous BO, right? And when we're actually trying to look at the actual objective of this optimization, we see a superior performance when we are using asynchronous Bayesian optimization, right? So clearly, this technique not only makes the utilization of resources more, efficient and effective, but also allows us to, get our, insights into the optimization scheme with with a lot more precision. So basically, there are many things that we have to do, from what we showed to where we want to be, which is basically building these self-driving metallurgical labs. They will have to have some type of Bayesian engine just because of, the expense associated with doing, actual discovery. But using these asynchronous methods will allow us to actually coordinate and orchestrate very complicated sequence of tasks in a much more efficient way. And with that, I would like to thank you for your attention, and I will be more than happy to answer questions after, the session, once the Q&A session starts. Thank you.
So thank you very much. Thanks for sharing with us your wonderful work. And now we are into the Q&A session. Is there any question from the audience?
Maybe Chris, if you can stop recording, please.